Okay, Hess's law. So, Hess's law of heat summation, we're going to go from reactants to products. The enthalpy change is the same whether reaction takes place in one step or in many. So that's what we were just looking at. So what's the chief use of this? Well, the chief use, calculation delta H for the reaction that can't be measured directly. So if we have a reaction where we're not able to directly calculate delta H, we can look at all the different thermochemical steps and set it up. Each step, summation, boom. Now we have the value for the reaction that we couldn't measure directly. So thermochemical equations for individual steps of reaction sequence may be combined to obtain the thermochemical equation of the overall reaction. So some rules. Whenever the equation is reversed, obviously you must reverse the sign. Okay, so if it was a negative delta H, it's now going to be a positive. If all coefficients of equation are multiplied or divided by same factor, the value of delta H must likewise be multiplied or divided by that factor. Okay, so if I need 2 waters, let's say on the product side, then I'm going to multiply the whole reaction by 2, then I'm also going to multiply the delta H by 2. Formulas canceled from both sides of the equation must be for substance in same physical states. Remember that state matters. So if it's a gas on one reaction and a liquid on the other reaction, then they do not cancel out. You have to atone for that difference in state. Okay. So strategy for adding reactions together. Choose the most complex compound in the equation for one-step path. Choose an equation and multi-step path that contains that compound. Write equation down so that the compound is on an appropriate side of equation. In other words, if I want it to cancel out, I want to make sure it's on the product side versus reactant side. It has the appropriate coefficient for our reaction. So if it's 2 in one reaction but only 1 in the other, then that's not quite right. I need 2 on both so they cancel out completely. Then what you'll do is simply repeat steps 1 through 3 for the next most complex compound, etc. Choose an equation that's going to allow you to cancel intermediates. Multiply by the appropriate coefficient, then you simply add the reactions together and cancel the like terms. Add the energies together, modifying your enthalpy in the same way that you modified the equation. If the reverse equation, then make sure you change the sign. If you double the equation, then double the energy. All right, let's look at an example. Calculate the delta H reaction for carbon as a solid and graphite going to carbon solid as a diamond. So given carbon plus O2 goes to CO2, that delta H will be negative 394. Carbon as a diamond then, adding O2 producing CO2 will give negative 396. To get desired equation, we must reverse the second equation and then add the resulting equations. So in other words, I want to multiply this guy by negative 1. So now I've got carbon solid plus O2 going to CO2 gas, and now I have CO2 gas going to carbon plus O2. That means I'm also going to reverse the sign. So now when I sum this up, I get carbon solid plus an O2 plus a CO2 produces carbon solid as a diamond plus O2 plus the CO2. And now obviously the O2s and the CO2s will all cancel out so that I'm left with the carbon solid graphite going to carbon solid diamond. I then sum up the delta H's and it tells me that's going to be 2 kilojoules. Hopefully that made sense. Okay. Again, if you have questions about any of these, feel free to email me to get some clarification. All right, calculate delta H reaction for 2 carbons plus H2 going to C2H2, given the following. So I've given you, let's see, they've given us the acetylene plus the O2 goes to CO2 in water. Notice it's liquid water. They've given us carbon as a graphite plus the O2 goes to CO2, and they've given us hydrogen plus oxygen gives us water. All right, now what we want to do is calculate the delta H for this reaction. So first off, we can see we have C2H2 right here on the reactant side, which means we're probably going to want to flip that because we want to get that to the product side, right? So keep that in mind. We'll have to be able to do that. We have carbon solid. We'll need 2 of those, so we'll probably have to end up multiplying this whole thing by 2. All right. And let's see, we have H2 plus half O2. So hopefully these halves of O2s and O2s are all going to cancel out in the mix. So let's take a look. All right, so we're going to take 2 CO2s plus H2O goes to C2H2 plus 5 halves of O2. That delta H for that reaction, that would be negative 1299, right? So just to get the acetylene on the product side, we're already at a positive 1299.6 kilojoules. Next, we want to multiply the C plus the O2 going to CO2 times 2. We'll do the same thing for the delta H. That gives us negative 787. And then last but not least, we'll take the hydrogen plus the oxygen to produce the water, and that'll give us negative 285.8. Now we simply want to sum these up. So a couple ways we can do this. We could list everything. So there it is. All our reactants. We have 2 CO2, we have H2O, then we have the 2 carbons, we have the 2 O2s, we have H2, then we have another half of O2. On the product side, we have the acetylene, we have the 5 halves of O2, we have the 2 CO2s, and we have the water. Now we can start looking at what's going to cancel out, right? So we have 2 CO2s, and we have 2 CO2s. We have a water here. We have a water there. We have 2 O2s plus a half O2 gives us 5 halves O2. That gets rid of that. And so now we're left with 2 carbons plus H2 goes to the acetylene. So we'll take plus 2099.6, add negative 787, add negative 285, and that gives us a positive 226.8. So what that's telling us is that to go with carbon plus hydrogen gas to form acetylene, it's going to cost 226.8 kilojoules of energy. All right, so hopefully you're able to follow along with all that. All right, which one of the following is a statement of Hess's law? Which of the following is a statement of Hess's law? So again, you can pause here if you want, read through each one. Let's see, for A, it says delta H for a reaction in the forward direction is equal to delta H for the reaction in the reverse direction. Well, that can't be true, right? We got to flip the signs. Let's see, delta H for a reaction depends on the physical states of the reactants and the products. The delta H for the reaction depends on the physical states of the reactants and the products. That's a true statement, but that's not really what Hess's law is talking about, right? If a reaction takes place in steps, delta H for the reaction will be the sum of the delta H's for the individual steps. That sounds like Hess's law. D, if you multiply a reaction by a number, you multiply delta H by the same number. That's a step we use while applying Hess's law. Delta H for a reaction in the forward direction is equal in magnitude and opposite in sign to delta H for the reaction in the reverse direction. Again, that's true, but that's not really summing up Hess's law, so we're going to have to go with C, right? Where if we look at the steps versus we look at a single step reaction, if it's the same reaction regardless of the number of steps, then the values overall will be the same. All right. Realistically on your test, I'm going to ask you to do something like this. Given the following data, calculate for the reaction 2 carbons plus H2 goes to acetylene. So given all that stuff that we just did, how would you get the answer, right? So you're going to flip it, add it, subtract it, multiply it, do whatever it is you have to do. You have 3 basic equations up top. I want you to use those to calculate the delta H for the reaction at the bottom here. 2C carbon solid plus H2 gas goes to acetylene gas. And hopefully you come up with 226. And of course you'll take the 1300 plus 2 times the negative 394 plus the negative 286. And when we sum those up, that should give us 226, right? All right, so tabulating delta H values. You need to tabulate the delta H values. The major problem is the vast number of reactions. We defined the standard reaction and we tabulated some of those. We use Hess's law to calculate delta H for any other reaction. So basically we tabulated a bunch of them that we could, and then we use those to then apply Hess's law and figure out other ones. The ones that we tabulated are going to be the enthalpies of formations, so delta H sub F. What this is the amount of heat absorbed or evolved when 1 mole of substance is formed at 1 atmosphere and 25 degrees C from elements in their standard states. Okay? Now remember, elements in their standard states have a delta H of 0. Okay, so that's going to be our standard heat of formations. So most stable form and physical state of element at 1 atmosphere and 25 degrees C. So for an element then, oxygen, its standard state is going to be O2 as a gas. Carbon will be a solid as graphite. Hydrogen, H2 is a gas. So again, H2 and O2 are diatomic. Aluminum would be a solid. Neon will be a gas. Note that all delta H formations of elements in their standard states will equal 0. Now, the funny part is if you go into the appendix and start looking at tables, you'll see that they still put it in there. So even if you forget for what the standard formation is for an element in its elemental state, you go to look it up, it's usually tabulated in there as 0. So you can laugh at yourself after you see it. You didn't remember. All right. So from our definition of delta HF, then we can write balanced equations directly. Right, so let's see. If we want to do the delta H formation of C2H5OH as a liquid, what we can do is look at some of these. So we can take 2 carbons plus 3 H2 plus a half of an oxygen, and that will make ethanol. Okay? The delta H of that formation is negative 277.03. Now, how did we get that? Again, you're going to go to the table, you're going to look up what the formation of carbon is, what the formation of the hydrogens were, what the formation of the oxygens were, and you're going to sum those up. Okay, that's going to give you the ethanol. For rust, Fe2O3, then what we'll do is we'll take 2 irons plus 3 halves of oxygen, goes to Fe2O3, and the delta H there will be negative 822.2. So what would a question look like? Which reaction corresponds to the standard enthalpy of formation of sodium bicarbonate as a solid? The delta H of formation is equal to 947.7 kilojoules per mole. So which equation corresponds to the standard enthalpy of formation of sodium bicarb? So remember, you want sodium bicarb as the product, so we can eliminate D. Let's see, A looks pretty good. All right, B's got some issues, and B is probably what can lead us to get into some trouble, right? So we did ionic charges in a previous chapter, and this will all be on the same test, so you got to kind of compartmentalize these things. We don't want any charges, all right? We want the elemental components when we're looking at enthalpies of formation. So as an elemental component, we get sodium solid, not as an ion, not as an ion, not as an ion, which pretty much made this pretty easy because right there is A is the only possible answer. All right, which reaction corresponds to the standard enthalpy of formation of C4H3Br2 and O2 liquid? So again, you probably want to start off looking for C4, right? So 4 carbons here. 8 carbons, 4 carbons, 4 carbons. Looks like we can get rid of B. All right, so we've eliminated B already. Let's see, then we have 3 hydrogens, but that's not how hydrogen comes, right? So now we've eliminated A. 3 halves H2, 3 halves H2. So far, so good. Then we have bromine. So if I go look bromine up, it's Br2. Is it a liquid or a solid? That's going to be a difference right there. And again, if you're looking at the charts, then you know it should be a liquid, which means my answer has to be C. All right. The standard enthalpy of formation of sulfur dioxide is negative 296.9 kilojoules. What is delta H for the formation of 16.03 grams of sulfur dioxide in its standard state from its elements in their standard states? Oh my gosh, that was a tongue twister. The standard enthalpy of formation of sulfur dioxide is negative 296.9. What is delta H for the formation of 16 grams of sulfur dioxide in its standard state from its elements in their standard states? All right, so they told us the value for the sulfur dioxide, and now we need to figure out how many moles are in 16.0 grams, right? 16.03 grams. So remember that kilojoules is per mole. The standard enthalpy of formation is 1 mole. So hopefully we get negative 148.4. The way we'll do it, we'll take again that 16.03 grams, we'll get that into moles, and then we'll get kilojoules per mole. So grams will cancel out, moles will cancel out, and we'll be left with negative 148.4 kilojoules. All right. So using delta HF, number 2, way to apply Hess's law without needing to manipulate thermochemical equations. So in other words, another way to get the delta H of reaction would be to sum up all the delta H's of all the products minus the sum of all the delta H formations of all the reactants. So let's consider a reaction. We have AA, right? So we have little a is the coefficient of species A, plus little b is the coefficient of B, and then going to C, which is the coefficient of big C plus D of D, right? So the delta H for that reaction would be C times the delta H of C plus D times delta H for the formation of D. We'll sum that. Then we'll subtract from that the reactants, A times the delta H of A and B times the delta H of B. At this point you have the units of kilojoules because all of these are going to be per mole when they cancel out with their coefficients, right? So when we multiply by the coefficient, that would be 3 moles times that many mole. All right, then all we have to do is sum it up for the products, sum it up for the reactants, and subtract the two. Delta H then has units of kJ. Delta H of formation has units of kJ per mole. All right, so I think we'll pause here and then we'll finish up with, actually let's do one example and then we'll pause and then we'll finish up with some more examples. So calculate the delta H of reaction using delta H of formation. So calculate delta H of reaction using delta H of formation data for the reaction SO3 gas going to SO2 gas plus 1/2 of an oxygen. So what we'll do is we'll multiply each delta H in kilojoules per mole by the number of moles in the equation. Then we'll add the delta H of formation multiplied by the number of moles in the equation of each product, and then we'll do each reactant. Then we'll subtract the two, right? So it'll be the summation of the products minus the summation of the reactants. So in this case, we'll have delta H of the reaction is equal to delta H of formation for the SO2. All right, it's already balanced, everything's 1 to 1, plus we'll do 1/2 the delta H of reaction for O2, and that's because we only needed 1/2 of the O2. We'll subtract from that the reactants, which in this case is the SO3. Now we'll plug in our numbers. We have negative 297 kilojoules per mole. That's going to be for the formation of the SO2. Remember, the oxygen's in its elemental state, so that's 0. And then negative 396 for the formation of the SO3. We sum that up and we get 99 kilojoules. All right? So hopefully this is fitting together and making some sense. And again, we're going to pause here because we're at about the 19-minute mark. The last segment will be all examples. So if you feel like you're getting the hang of this and you want to skip that next segment, that's up to you. I would suggest you go through it fast. If you go don't skip it all together, but if you want to go through it fast, just to make sure you're hitting all the points, it's just going to be example problems using Hess's law. All right, see you soon.